Okay, today's lecture topic will be about the S-domain circuits. So it's basically circuit analysis, but we will use our own domain like S-domain instead of what we used to do in the previous circuit like phasor domain. Or sometimes when we do some transient circuit analysis, how can we do first order, second order, or higher orders using S-domain other than we don't need to use the differential equation. Okay, so as usual, let's write the outline. For today is Monday, the page from 131 to 134. Then in Wednesday, we will continue on the S-domain circuits. Then page 131, 134, basically it will be more examples about S-domain. And also the due date for homework number 10 and homework number 11 will be on Wednesday. And keep in mind, homework number 11, no solution. The solution is already posted there, but I encourage you to try by yourself and see how you can answer. Then look at the solutions and compare your answers with the solution. Then on Friday, the 22nd, is the lucky day, which is the exam. Next week, Monday, the 25th, we will start a new chapter, which is chapter 5, a new topic other than Laplace transformation, which is 46. Something more fun. Okay? Now let's start the lecture, which is S-domain. It is just a circuit analysis, but I would say let's include signals in circuits. So S-domain circuits. Okay, so the circuit elements, as we know, it can be either sources or passive elements, right? Sources like what? Voltage source, current source. And those sources can be either independent or dependent, right? So it can be independent voltage source, independent current source, or voltage dependent voltage source, voltage dependent current source, current dependent current source, current dependent voltage source, something like that. Then for the passive elements, it can be like what? Inductor, resistor, capacitor. Why passive elements called passive? What's the point? Why not active? Why not something else? So passive elements means the energy that cannot produce, the device that cannot produce energy every time consumed. So every time the resistor will consume energy, like a light bulb, every time consume energy. Capacitor, inductor, it will take energy, so it cannot produce energy. So even though the inductor and capacitor can be charged and release, charge and release, charge or discharge, but they're still considered as passive elements because they cannot produce energy. So basically, we will say passive elements, any device that cannot produce energy. While you might hear in the future, when we go for more advanced courses, you might hear about something called active elements. So active elements, these elements that there's some way to produce energy. Basically, they will be connected to some sources that these elements can inject energy to somewhere. So whereas it has the capability to inject energy by itself without the need to be connected to any other elements. Okay, so passive elements. They are resistor, inductor, capacitor. And we know those from circuits analysis. We know resistors in ohms, inductors in henries, capacitors in farad. So in circuit analysis, when we do the AC circuit analysis, we said to avoid the differential equation, we created our own version in domain which is called phasor domain, right? And phasor domain that we created makes the life easy to deal with the circuits by converting the circuit to be a complex numbers. So basically we converted R in phasor domain to be R. So this is the impedance of the resistor. Then we converted inductor to be as J omega L. So this is the impedance of the inductor. Or sometimes we can call it JXC, JXL. Then C for the capacitor, 1 over J omega C, which is C capacitor, in other words, 1 over JC, something like that. Yes, that's what we know. So that was in phasor domain. That was in circuit analysis. Then we did several analysis about it, and it works perfect. Now, in our consideration, we will assume some more advanced things. So basically, phasor domain was valid at steady state. Steady state analysis. What does steady state mean? There is no switch action. Steady state means everything working fine without having any problem. Now, in signals analysis, we'll try to expand this. I would say what we've learned in circuit analysis is still true, but if and only if steady state. If there's transient, then there will be some other considerations. Then the inductor might not be only J omega L. It will be with something else. Something else like what? It might be depending on the initial condition. How is the status of the inductor? It might be fully charged, it might be fully discharged, it might be half charged, half discharged. The same thing for the capacitor. So whenever there is a transient, this means there's something happening, something going on. And as we know, in circuit analysis, the transients means there's a switch, right? Switch on and off. So if there's a switch on and off, and in AC circuits, this means there will be some problems. So what we've learned in phasor domain, we need to expand the elements, give more room so we can get a better approach. Therefore, in order to deal with transients, I don't recommend to use phasor. We need to use our own or use the original thing, which is called Laplace transformation. Actually, I would say the phasor domain is a special case of Laplace transformation. Then let's go to the original case, which is S domain. So now I'm going to talk about S domain, how to convert either resistor, inductor, capacitor from time domain to S domain. I'm no longer talking about phasor domain. I'm talking about the overall topic, or the overall idea, which is S domain. So let's start with the resistor. We know the resistor in time domain, I would say time domain as TD, S domain as SD, something like that. We know the symbol of the resistor, the resistor. This is the current I of t. This is plus minus the voltage V of t, and this is the resistance. Since the current enters the positive polarity of the voltage, therefore this needs Ohm's law to be positive. As a result, Ohm's law of V of t will be I of t times R. We know this from circuits. Then, when we convert this to S domain, how will it look like? It will look like, here is a resistor, this is plus, minus. It will be uppercase V of S, here it was lowercase in AC, but in S domain it will be uppercase V of S, and here is I of S, uppercase. Okay? Remember, in phasor domain we used to put them uppercase, now here in S domain we will put them uppercases. In phasor domain, we used to put bars here. In S domain, there is no need. In phasor domain, we put bars become the complex numbers. Here, it's enough just to make it like this. In S domain, don't put bars above this complex. So how to apply Ohm's law? Ohm's law, V of S equals to I of S times R. Okay? So the overall thing, the resistor in time domain, S domain, they are the same. No change. And the units, of course, here, ohms, ohms. So, as we know, the resistor in phasor domain, there was no change, and the same thing in S domain, there is no change. Just change the symbol V of S to be V of t, V of S, I of t will be I of S. Okay, this is the simplest case. Does this make sense? Okay, good. Now, the other thing, which is the capacitor. In time domain, we used to say, here's the capacitors. simple. This is V of t, then I of t here, or I would say I of t. This is I of t. Then this is the positive and the negative. The current enters the positive, that's our target, so we can make the positive sign. If the current enters the negative, then there will be a negative sign in the formula. And what's the time domain formula? I of t equals to what? C dV by dt, right? That's what we know. Now, there is another formula. If you need to find V of t, it will be 1 over c, the integral between 0 to t, I of tau, d tau, plus V of 0. Okay? Just do the integral to find V of t. Now we know this from circuits. We know how to find I of t, how to find V of t. Now, how can I convert this into S domain? In phasor, we used to say 1 over j omega c I. Here, actually, it will be different. Why? Because we are going to assume here not steady state. This is not steady state approach. It can be either transient. We're talking about the overall here. So since it's not steady state, I cannot guarantee the initial condition. The initial condition might not be 0. It can be any other value. It can be changeable. So, in order to convert this, let's look at the current formula. Try to do the Laplace transformation. Laplace transformation for I of t is I of s, right? Laplace transformation of the constant times the derivative, the constant will remain. The derivative will be what? S, V of s, V of s, minus V of 0. Is this correct? That's the Laplace transformation for the derivative. Now, I will say that I of s will be c times s V of s minus c V of 0 negative. Okay? Does this make sense? That's Laplace transformation when we did this transformation. This is, I would say, approach A. Now let's deal with approach B. Basically, I need to convert this expression into Laplace transformation. So V of t will be V of s, 1 over c remains. Then the integral is basically denoted by 1 over s, I of s, plus V of 0, it's a constant, so the constant is actually, I would say it's times u of t, then it will be V of 0 over s. V of 0 negative over s. Then this is the second equation, which is approach B. Now look at the capacitor. We have approach A, approach B. 2 equations, which means 2 different models. Depending on, am I using the current model or the voltage model? So let me draw the both models for each one. So here is model A, which is based on I of s equals c s V of s minus c V of 0 negative. So how this will look like, it will look like, this is the capacitor, then we have a current source that goes here. So we will say, this is I of s, this is the capacitor, which is 1 over sc alone, this is the current source C V of 0 negative. So here's the evidence. That's how it looks like. This is our evidence. That's the model A. Again, this is in terms of currents. In terms of currents. Now we have another model B, which is V of S will be 1 over C times 1 over S I of S plus V of 0 negative of S. So how this looks like, this one in terms of voltage, then it will be as a capacitor in series with a voltage source. So this is 1 over S V of 0 negative, this is 1 over SC, then here is I of S, here is I of S, and here is plus minus V of S. Okay? And for the top button, for the top, all this plus minus V of S. Now, the capacitor is no longer 1 over J omega C. It is 1 over SC, and there is either a current source or a voltage source. Which one should I use? Whatever you more convenient for you. If you have the initial condition of the voltages, use the voltage model. If you have the initial condition of the currents, use the current model. Okay? That's how we replace the capacitor. Again, here I'm talking about the overall model. If it is transient, if it is steady state, it should be true for any situation. While what we have learned in circuit analysis in phasor domain, it was valid only at steady state AC circuit analysis. If you go to the textbook of circuit analysis, you will see the chapter named Steady State AC Circuit Analysis. And again, this one it's the general model that can work even if it is DC, if it is AC, if it is steady state, if it is transient. So this is the generalized model. Okay? Now, how can we validate the phasor domain in this situation? How can we say that, okay, we used to say the capacitor is 1 over J omega C. I'm going to say, assume zero initial condition. Okay? What will happen to the models, both models, model A or model B? Model A will be like this, 1 over SC. Model B will be like this, 1 over SC. Both of them will be like this. Look at the current source. If the voltage source is 0, then just remove it. If this one is 0, just remove it, right? Initial condition. So this yields to be only that capacitor model with 1 over SC. Okay. We know S equal sigma plus J omega, right? Right? Assume another assumption. Sigma equals 0. This yields S equal to J omega, right? Then 1 over J omega C, or 1 over SC is actually 1 over J omega C. And this is what? Phasor. Yeah? That's it, right? So that's how we recognize that the phasor domain is a special case when sigma is 0, when 0 initial conditions. So what concerns us, or what matters with us, or what's happening, what's the change between this model and the others, which is this model, by making it more generalized, by not assuming 0 initial condition. That's it. So 1 over SC is the same, can be 1 as 1 over J omega C, if and only if, assuming the real part is 0 or that. How about DC? DC, omega equals 0, right? Or frequency equals 0, this is omega equals 0, then 1 over 0, this will be infinity, which means open circuit. That's why we used to say the capacitor is open circuit, right? So that's why I'm talking about. This model is generalized. It can be valid for DC, can be valid for AC, for both of them, no matter if it is transient or it's non-transient, if it is steady state. Okay, that's about the capacitor. Now let's discuss about the third thing, which is the inductor. The third equipment, the inductor. In a similar way, for the capacitor, there will be two forms, form A, form B, depending on voltage or current. So here's time domain. It is I of t, L plus minus V of t. So according to our analysis, this will be V of t equal L di of t by dt, or we can say I of t equals 1 over L, the integral from 0 to t, V of tau, d tau, plus I of 0 to t. So we have both models. How can we find them? You can just basically convert this to Laplace transformation. Do the Laplace transformation from model A. It will be V of s equal L s I of s minus L I of 0. So what matters with us is the initial condition. The second one, I of s will be V of s over SL plus I of 0 negative parts. Because integral 1 over s and there's 1 over L, then that's how we get it. So again, this is model A, this is model A. Now, how can we draw the model A and model B? Here is A, here is B. Then model A will be the inductor, that source. Model B will be inductor and current source. So that inductor is that basically SL. That source is L I of 0 negative for model A. For model B, this is SL. This is I of 0 negative over S. Then here plus minus V of t. And here is I V of S. V of S. And here is I of S. This is again I of S. And this is like all voltage plus minus V of S. Okay? That's what we have in both models. Now, assume 0 initial condition and S equal sigma plus j omega. So we'll assume again sigma equals 0. This yields S equal to j omega. As a result, this yields to only j, or sorry, this is SL equals to j omega L, which is the same thing that we know in phasor domain. Okay, that's why it's just to say phasor domain is a special case when we assume 0 initial condition and we assume sigma equals 0. Okay, any question? So now we have the models of 3 passive relays. Now we know from circuit analysis a definition is called impedance. What's the impedance? What do you know about impedance? Yes.
It's like complex resistance.
It's like complex resistance, which is basically when we convert everything to phasor domain, we would like to see the impedance of the resistor, the impedance of the inductor, and the impedance of the capacitor. So we used to say R or j omega L or 1 over j omega C. Now in S domain, we need to say what's the impedance. We realize in these models, when we convert the capacitor and the inductor, the capacitor will no longer be capacitor. It will be capacitor and the voltage source, or capacitor and the and current source. Inductor will no longer be inductor alone. It will be inductor with current source, inductor with voltage source, whatever. So the thing here, what should I consider the impedance? Should I say the impedance including these sources, or should I remove these sources? Or in other words, what's the definition of the impedance? So now we're gonna redefine the impedance definition. So this is in page 153. So the definition of the impedance. We will have more definitions in Laplace transformation. So basically, the impedance in S domain can be defined as it is voltage to current ratio in the S domain circuits with under zero initial conditions. So basically the impedance says that, okay, let's use the models that we know from S domain for both inductor or capacitor or resistor, assume zero initial conditions. In other words, this means I of 0 negative equals to 0, and the same thing for V0 negative is the same equal to 0. Okay? So just keep in mind under zero initial condition. So we will say in S domain, the impedance, I'm no longer, I'm going to say like Z bar, because here S domain. So I just want to distinguish between S domain or phasor domain, so I'm going to make it as Z alone. Z sub R, it is VR of S over I of S when initial condition equal to 0, which is going to be R. How about the capacitor? Z capacitor, V C of S over I C of S when initial condition is equal to 0. This yields 1 over SC. Okay? Then Z inductor, VL of S over IL of S when initial condition is equal to 0. This yields to be SL. So now the impedances are no longer, as we used to say in phasor, 1 over j omega L, 1 over j omega C of j omega L. We will say SL 1 over L or 1 over S. Okay, so take it as a rule. Then again, like phasor domain, S equal sigma plus j omega, so sigma equal 0. This yields, this will be R, this will be 1 over j omega L, this will be 1 over j omega C, and that one will be j omega L. So again, phasor domain, only a special case. While this one is the overall model. Now, how can I solve this circuit when we have an S domain? Basically, you're going to convert everything to S domain. Whenever you see inductor, convert it to model A or model B. Whenever you see capacitor, convert it to model A and model B. Okay? Now, to summarize these models, you can refer to, go to table 4.1. This is very important table, and we're going to use it a lot when we do the circuit analysis. Basically, you are not required to save or memorize these models, or even you are not required to write this in your note card. This table will be provided to you. How the table looks like, I think I have it here. This is it. This is how we find the S model for the resistor. This is the S model for the inductor based on model A or model B. This is for the capacitor. So you already have those. Your target is to use these tools in your circuit analysis, not to memorize them. These tools will be provided to you. So even when you go to the test or to the, if there's any quiz or anything, this will be provided to you. So don't worry about memorizing this. Just learn how to use this. Okay, does this make sense? Any questions? Let's go back to it. Then again, our target is to solve circuit analysis, no matter is it transient or non-transient, which is steady state, or no matter is it DC or AC. This should be valid everywhere at any circuit. Now let's do an example. Solve for I of t. Most likely, we prefer when we have AC, steady state, AC circuit analysis to use the phasor and just we don't need to use tables or Laplace transformation. So we prefer, whenever we are dealing with steady states, let's use the phasor domain, it's much easier. But this does not mean the assuming is not true. But anyway, here in this circuit, in this course, we'll assume only assuming. But in practical life, I might not need to use this one. I can use physical and that's it. But anyway, let's deal with this circuit. Here's plus minus the inputs. And I'm going to assume the input as 1 volt, which is basically DC. DC circuits. There is a switch. Switch will be closed at t equals 0. This means it is transient. It's DC transient problem. Then we have a resistor, R, then an inductor, L. So R equal to 10 ohms, L equals to 1 Henry. Then the current here, this is I of t. So my target is to calculate I of t. Okay? How can I solve this circuit? I need to calculate I of t as a function. So again, this is DC circuit transient. According to the circuit analysis, it is first order. So we can either solve it using first order differential equation, or we can use the circuit techniques, which is by assuming each general solution and try to find the initial conditions and substitute it over the general formula. That's one way. But now, let's use our own way by making it much easier. So the first thing that you need to keep in mind, we need to convert this to phasor. I'm sorry, to estimate, which is Laplace to me. To convert this, remember, we have inductor. Inductor, this means we need to have initial conditions, so it can be either voltage model or current model, right? So we need to know the initial conditions. All right, here the initial conditions, are those provided? No, they are not provided. What should I do? You need to find the initial conditions by yourself first. How to find them? Before the switching action. So, calculate initial conditions first. So when t less than 0 before the switching action. So I'm going to redraw the circuit. Here is 1 volt. Here switch is open. This is resistor. This is inductor. Now here is I of t. What do you think I of t will be? 0. Right? So I, when t less than 0, equals 0, or in other words, I of 0 negative equal to 0. Now I know the initial conditions is 0. Then I'm ready to do the transformation. But before doing the transformation, Laplace transformation, I will say, can I do the Laplace transformation for 1 volt? Yes, it's a constant. I can find it. Can I do the Laplace transformation for the R? Yes. Can I do for the L? Yes, and I have the initial condition. Can I do it for the switch? What should I do? Any thoughts? So to simplify the circuit, so I can be able to solve this using the estimate since the switch is non-linear. Any thoughts? There's a trick, easy trick. Using the signals. Using what we've learned from step function or impulse or ramp. What do you think? We will use a step function. How? Look at this part. If the switch is off, the output is off. If the switch is on, the output is Vn. So, I'm going to switch on, then it will be Vn. Switch off, it will be 0. Switch on when t larger than 0, switch is off when t less than 0. In other words, it will be like this, this. What does this mean? Step input, right? So this means it is V inputs times U of t. V input of t times U of t. Now, we're going to use the signals into the circuits. Now, if this example is interesting, then I'm going to model what's inside the circle to be only a source and times U of t. So the circuit will be like this. V inputs t times U of t. Here is resistor R equal 10 ohms. Here is inductor L equal 1 Henry. And my target still need to calculate I of t. So you see the inputs times U of t, this in other words equal to 1 times U of t. Because V will equal to 1. Now I avoid the nonlinearity of the switch by making it by a function that we are already familiar with it, which is U of t, and we know how to find this the Laplace transformation, right? We know how to find the Laplace transformation. So that's good. So the next thing to solve this circuit after we did convert, or we said that this is U of t, do you know how to find the Laplace transformation of L? Yes. Do we know how about the R? Yes. About V, yes. So I'm ready to do the Laplace transformation. And I already have the initial conditions. Then I can be ready to convert this circuit to estimate. So remember that L equals 0 with I of 0 equals 0. Since the initial condition is 0, then the equivalent model for the inductor will be SL, right? Because the initial condition is 0, then just remove it. So I'm going to write, which is plus minus. This will be Vs. Then here R. Then this will be Sm. Okay? So let's substitute the values. R is 1 ohms. R, as the main R. The inductor, instead of L, will be SL. What's the value of L? Is 1 Henry. S times 1 is equal to S. How about Vs? It is U of t. U of t, Laplace transformation of U of t is what? 1 over S. Is this correct? My target is to calculate I of t, so it will be I of S. And remember, here we are not in phasor, so don't put bars above these lines. How can I calculate I? Now it's a circuit analysis. Very similar to phasor, but now it's in S domain. How to find I of S? Any thoughts? This is a circuit. We know the voltage source, 1 over S. We know R, 1 ohms. We know SL. How to find the currents? You know? Remember, S here with 0 initial condition, therefore there is no voltage source, no current source. So my target is to calculate I of S.
Find the equivalent impedance.
Find the equivalent impedance. That's one, correct? KVL, whatever you want. Apply the circuit techniques. KVL, equivalent impedance. So let me say, I'm going to do KVL as an example, just to make it simpler. While equivalent impedance might be easier, actually. But I'm going to do the hard way. So it's negative V of S plus I of S times R plus I of S times SL equals 0. And my target is to find I of S, so I of S will be V of S over R plus SL. Or in other words, voltage over the equivalent impedance. Then substitute the values. V of S is actually 1 over S. Divided by R is 1 plus SL, which is S. 1 plus S. Okay? Here is it 1 Henry or 2 Henry? Inductance. Okay, 10 ohms. Yeah, that's right. It's okay. 10 ohms. Okay. And here this is 10 ohms. Now, let's make it better in denominator and numerator. So it will be 1 over S times S plus 10. Or in other words, 1 over S squared plus 10S. That's I of S. Now, I'm done with the most important thing, which is how to calculate I of S. What left? We need to convert this to time domain. If we are in phasor, it is easier to do that. But now it's a Laplace transformation. So how can we convert I of S to I of t? Let's apply what we have learned before in the previous lectures, which is partial fraction expansion, right? So first, make sure, is this strictly proper? Yes, it is. Then let's do partial fraction expansion. So we can say I of s, which is 1 over s plus 10, equal to C1 over s plus C2 over s plus 10. Now just signals. So now we've moved from circuits to be signals, or which is this example is cumulative equilibrium. So I have to find, let's find C1. C1 is actually s times I of s when s equal to 0. Then it's going to be 1 over s plus 10 when s equal to 0, which is 1 over 10. How about C2? C2 is s plus 10 times I of s. Substitute when s equal to negative 10, then it's going to be 1 over s when s equal to negative 10, then it will be negative 1 over 10. As a result, we will say I of s equals to 1 over 10 times 1 over s minus 1 over s plus 10. Just I took 1 over 10 as a factor. Now, I'm ready to do Laplace inverse. So when you do Laplace inverse, I of s will be I of t, which is Laplace inverse of I of s. Then it's going to be 1 over 10, 1 over s, which is u of t, 1 over s plus 10, here minus 10, so minus e, or 10, t, u of t. That's it. So we can say I of t equals 1 over 10, 1 equal negative 10t, then put u of t here, amperes, that's the final answer. Or if you want to write it as, you can say I of t equals 0 ampere when t is than 0, or 1 over 10, 1 minus equal negative 10t amperes. When t larger than 0. Okay? Well, I mean, that's enough just to answer the black box. So here we applied signals and circuits. So now what we've learned before, it used to be pure math. Now we're gonna use this in here. Okay? That's maybe the difference between what you've learned in the function quotient, Laplace transformation, and here we are trying to put more in applications. Any questions about this example? So the first thing, we model the switch as a u of t. The second thing, we need to find the initial conditions if it's not provided. Then we need to convert the circuit, every element to Laplace transformation, do KVL, KCL, Ohm's law, whatever you need, nodal, mesh analysis, etc. until calculating the currents or the voltage or the required thing, then do Laplace inverse. So you are required to know the nodal analysis, mesh analysis, source transformation, all of the circuit techniques. Circuit is a prerequisite to this course. So you need to be familiar with this. If not, please go back and check the circuits. We will not make it too hard. It's not like too challenging example, but keep in mind you need to be familiar with everything, and you are required to do this during this course. So we will see, as we'll see some examples, we will do some mesh analysis, we will do node. I'm not sure if we will do super, non-super mesh, but just make sure as a precaution before you do all of these circuit techniques. Now, let me do one more example, and I'm going to do it in fast way, by not justifying things. The previous example, I tried to over-justify just to make sure you understand the concepts. Now, so you already got it, but let's go and do some simplification. So here's a voltage source, 10 volts, and it is DC circuits. AC, it will be just more complicated by converting the cosine to mean that voltage expression as over s squared plus b squared. Here is 8 ohms, and the switch is actually closed, then it will be open at t equals 0. Here is a capacitor 3 over 8 farad, then a resistor 2 ohms, inductor 1 over 3 Henry, plus minus 20 volts. So the concern or the question is to find this current.
Is that Henry or millimeter?
Henry, not Henry. Just like so. Might not be realistic, but just assume it's circumstances. Now we need to convert this or to solve these circuits to find I of t. So the first step, let's try to model the switch, or before model the switch, first step, look at the initial condition. Second step, try to get rid of the switch. So sometimes, some problems, the initial condition will be provided, then you can skip this step. Maybe in the textbook, you might see some problems that the initial condition provided, then you need to do the step number 1. So let's do the initial conditions. Before the switching action, which is at t equals 0 negative, before the switching action. Here, it's DC circuits. Since it's DC circuits at steady state, this means the capacitor is open circuit, the inductor is short circuit. Again, how can I guarantee this? We know SL equal DC S equals 0. So SL will be 0, therefore it's short circuit. SL equals 0, this is for its short circuit, while 1 over SC, which is 1 over 0, which is infinity, this means open circuit. This is if you need to do it out. If you don't, just say like the inductor is short circuit, capacitor is open circuit. And apply the initial switch status, because if we are to do, we need to do the initial switch, the initial condition. So the initial switch status is closed. Here is 10 volts. Here is 8 ohms. The switch is closed. Now the capacitor is open circuit. Here is the resistor 2 ohms. The other inductor is short circuit. Then when we here is the source plus minus 2 volts. Now what do we need to do? How many storage elements we have? 3. 3 ohm. 2 actually. Inductor and capacitor. So let's find the initial condition associated with the voltage of the capacitor and the current of it. That's my target. How to find this? So basically, it is closed circuit. I mean, it's closed path, so there is a current. Definitely IL exists. How to find IL? Nodal analysis or KVL, whatever it is. Something that we learn from nodal analysis. You can say that IL of 0 equal to 20 minus 10 over the impedance between them, which is 8 plus 2. If you're still unsure, then the KVL. Basically, KVL, outer row, which is negative 10 plus 8 times IL of 0 plus 2 times IL of 0 plus 20 equal to 0. This yields IL of 0 negative will be 20 minus 10 over 8 plus 2. So the answer will be negative 100. 10 minus 20. 10 minus 20 will be able to help us. So it will be negative 1 ampere. Okay, does this make sense? Again, please make sure to go back and review the circuit analysis, the nodal ordination. So here I did KVL out the output. This is the output. Now, the next thing we need to calculate is VC of 0. So I'm going to do KVL at this point. So KVL, go to, start from the left bottom corner, do chop clockwise, so it is negative VC of 0 plus IL of 0 negative times 2 plus 20 equal to 0. Therefore, VC of 0 negative equals to IL of 0 negative times 2 plus 20, and we already calculated IL of 0 is negative 1, which is negative 1 times 2 plus 20. So the answer, VC of 0 negative equals to 18 volts. Okay? Now I know the initial conditions. I just found the initial conditions for each element because we have 2 storage elements, inductor and capacitor. Then I'm ready to do the next step, which is how about the switch? What will happen to the switch? So I'm going to study what will happen after the action. After the action, the switch will be open. When the switch will be open, what will happen to the wrist? If the switch is open, so since the switch is open, we can neglect this, right? Because it's open, right? So I'm going to look at the circuit, look at this part. That's what we need to do in the Laplace transformation. So basically, we're going to write the values. So here this is 3/8 capacitance. And the resistor here is 2 ohms. This one is 1/3 Henry. Then this is 20 volts. And we will keep in mind, since after the switch, we will put 20 volts times unit, because we did after the switch action. So 20 times unit. Because this is after at T, which is 55. So let's stop here. Then next lecture we will continue. So